Thank you very much for the introduction and for the invitation to speak at your wonderful workshop. My name is Kontschieder. I'm the Director of Research of Mapillary, and today I'm going to talk about computer vision with less supervision. For those of you who are not familiar with Mapillary, Mapillary is the street-level imagery platform that scales and automates mapping. What does this mean? So this is a view of the coverage where we have imagery on the global scale. And clearly, Mapillary is a data platform. So every green dot that you see here has some form of imagery on our platform available. Now that data can actually be contributed very easily by everyone. Actually, anyone with a camera and a GPS track is able to provide imagery to our platform. That obviously is heavily used by people who are using phones, action cameras, but also dash cams, vehicle sensors, and professional rigs are actually used for providing data to our system. In such a way, we could collect already more than 1 billion images, and we're covering more than 10 million kilometers of road being mapped. With all that data, what we actually do is process it and extract what we call map data. And that map data is obviously being collected at scale from the street level imagery. What you see here is a visualization of a number of map features that we have on our platform. For example, there's trash cans, there's column poles, there's benches, there's junction boxes, traffic signs, and many other objects that we detect in the images that we can position based on image-based 3D modeling that we're running at large scale and eventually put as map features on the map. So the Mapillary ecosystem looks as follows. On the bottom, you see actually is where we have our contributor network located. So this is the basis from where everything begins and how everything starts to roll. The contributors are providing us images and image data to the platform based on which we run 3D modeling. We have object recognition algorithms in place that run, for example, panoptic segmentation, which identifies object instances and stuff category segments in the images that we have, that we run the algorithms on. And then combining the 3D information with the extracted map objects, and when combining the 3D information with the extracted object segments, we can derive map features that we eventually put on the map. So what can be clearly seen is that we have a very strong dependence on object recognition algorithms. And those algorithms are usually trained in a fully supervised way. So here we can see some of the applications. When the images come in, we run semantic segmentation to extract 97 object types. But we also use those recognition algorithms to perform anonymization for critical and sensitive areas in the images, like license plates or faces. We also exploit the object recognition pipeline for traffic sign recognition. And today we're recognizing around 1,500 types of traffic signs all over the world. When joining the information about the semantics with the 3D reconstruction, we get something that we call a semantic 3D point cloud. And with that point cloud available, we're actually able to extract the map features that we are able to put on the map. Now, a lot of these algorithms that are in place require to be able to be on top of the state of the art when it comes to research in computer vision. And research in our team is mostly driven by people shown on the slides, even though we have a number of other people who are working on the boundary of research and application. And lots of the things that I'm going to show in the next slides is actually wonderful work done by those people. And I would like to use this opportunity to also thank them for their fantastic work. As you've seen before, Mapillary actually is a huge pool of data. And in that pool of data, we started a couple of years ago with a project that we called the Mapillary Vistas Dataset for semantic understanding of street scenes. And the semantics come into play because we were developing an annotation workflow that allowed us to annotate 25,000 images that we selected carefully from the distribution of data that we have on our platform. And we've been annotating those images such that we could derive 66 different object types for the publicly available research version and 152 object classes for a commercial or internal usage. Out of those 66 available research categories, 37 are instance specific, which means we have individual instances of objects annotated. With that data set in our availability, we were able to produce something that's more complex and more varied than many other available data sets. And this can be seen in some of the visualizations here. So not only do we have very diverse viewpoints from the roads, but also from sidewalks and off-road, but we've also captured data in many different areas of the world with various weather conditions and capture times, and very importantly also from many, many different camera types, since we're not usually aware or not in charge of what type of camera models people are using to collect the data that they upload to us. Now, while this is clearly not the focus of this talk, because we want to talk about learning with less supervision, this is what empowers us to drive two projects that I will describe a little bit more detailed in the remainder of my time. The first one is called single image, or is related to single image depth estimation. And the second is multi-object tracking and segmentation. And what we're now doing is we're departing from that very heavily manual annotation workflow to something that can be extracted in terms of data in almost a completely unsupervised way. So let's start with the Mapillary planet scale depth dataset. This is going to be a new dataset that we will release for actually learning deep learning models in order to produce metrically accurate depth predictions. And we want this data to be suitable for real-world application, which means it should be large, it should be very complex in terms of the environments and diverse, the ones that we're using to produce that data. It should contain data from all around the world. It should contain many different camera types with their different focal lengths, distortion characteristics, with the type of sensor noise that we see in all of these images. And we, of course, want to stick to having lots of different weather conditions, times of days, viewpoints, and so on. Now, when we started designing that data set, one of the things that we had to sort of agree on was that we wanted to put a number of constraints in order to produce very high quality depth data. And some of these constraints are listed here. So first of all, for the areas where we pick sequences from our platform, we wanted the data to be densely available. So at most 5 meters between GPS positions of available camera frames. And the camera turning angle between adjacent frames should not be more than 30 degrees. We also want the cumulative trajectory in the actual sequence that we use to be larger than 70 degrees in order to better constrain the focal length. Now, one important fact to remember is that the data uploaded to Mapillary does not come with any camera calibration parameters. So we need to determine these by ourselves. And we do that by running an iterative way of estimation for those parameters. We initially start an SFM algorithm. We use OpenSFM, which we're a heavy contributor to, and apply a set of default intrinsic parameters. We, for example, set the focal length to 30 millimeters, and we assume no radial distortion. The focal length and the first two distortion parameters of the Brown model are then optimized during bundle adjustment. So we have a first iteration of SFM that then provides us with an initial set of camera parameters. And as we use those parameters to reinitialize in a subsequent iteration of running SFM, what we get is a refinement of those parameters for specific camera types. Now we know that, for example, even the same camera, when being manufactured, obviously has some deviations in the camera fabrication. So we also know that some of the parameters might not be ideal for every different instance of the same camera. However, this is something that we ignore, and after running 10 reconstructions for the same type of camera, we apply a hand selection for the final reconstruction, and then apply those parameters to all the different camera types. In this slide, we show that we have a very broad geographic distribution. So for example, we're imposing a global prior that involves having 20% of the data coming from North America or from Asia, 15% from South America, 20% from Europe, and so on. In order to do so, we've been imposing a regular grid on top of the globe. And from those cells, we try to homogeneously sample our data. We've been running the camera calibration process that I mentioned before for 250 camera models in the final data set. And altogether, we've been producing 750,000 images with depth training data. Now, one important part that I mentioned before is that we want to be able to obtain metric scale and dense depth information. So what we're actually doing in order to get rid of the scale ambiguity, which is inherently available when running SFM, we were also introducing the information from the GPS signal. So in the bundle adjustment, we can actually add a cost term that is proportional to the square distance between the initial noisy GPS and the actual estimated camera positions. So in that sense, we can actually better constrain the resulting scale of the 3D model. We've been in addition removing outliers, which are, for example, due to short sequences, or reconstructions by which the most distant cameras are not more are closer than 20 meters. So we're just discarding those. Finally, since SFM initially just provides us with a sparse reconstruction, so with only sparse matches, we're running a densification in terms of multi-view stereo patch match algorithm. And from that algorithm, we're actually able to derive dense depth data for more pixels in the image. Now that patch match algorithm may still produce spurious results, but since for us it's very important to produce high quality depth data, we're running some additional filtering of the dense depth results. So in that slide, we can actually see the candidate image on the left, top left, and a map that's a co-visibility map, which actually indicates in how many adjacent or neighboring images in the sequence we see the same pixel as well. So you can see that there's some variability, and in the end, what we're imposing is additional checks in terms of consistency of the actual available depth, and constrain such that we have at least 5% of pixels filling valid depth information. This is the overview when in comparison with other currently available data sets for training depth estimation algorithms. So the most related one is probably megadepth, which is almost is the penultimate row in this top table. You can see that the number of images there is smaller than ours. It's also produced by using an SFM pipeline. But ours is not only larger in extent, it also has a much more broader setting in terms of the extent. So we're using a total of 50,000 scenes from all over the globe. And in addition, we can produce metric depth. On the bottom, we can also see the distribution of volume normalized depth for different data sets. Now, one of the important pieces that we have and that we need to consider is how do we actually train a model with multiple cameras, with different types of cameras. And what we're coming up with is a very simple but effective way of running normalization, which we call camera normalization. So we are essentially applying a canonical camera model normalization, which eventually leads to resizing of images because we're imposing a fixed focal length that we normalize to. we assume to be given a square pixel sensor and no radial distortion. And for example, when, for example, running experiments on the KITTI dataset, there's a fixed focal length of 720 pixels. This is our reference focal length that we applied. And when constraining the camera in that sense, eventually what is left for the network is to estimate the real-world sizes of objects. This is our experimental setup. So we are using a unit architecture, which is ResNet 50 based. On top for the prediction, we apply a DeepLab v3 head. And what actually happens is that with the type of output stride that we have, so an X16 downsampling, we require 4 stages of upsampling. The first 3 of them actually happen in stages. And in between those stages, we're concatenating the outputs with the corresponding features from the encoder part in the skip module. The final upsampling is done by running bilinear X2 upsampling. So finally, we're predicting the logarithm of the focal length normalized depth and apply something that is called an eigenloss, which is actually also related to the C-log measure that is typically applied when comparing results. So in this table, we see our obtained results, and we've been running quite a battery of different experiments. The most related data set to ours is, as I mentioned before, MegaDepth. And what we do is we apply different types of normalization strategies. One of them would be just a naive one, where we don't apply any kind of normalization at all. The other one, depicted as CC, is referring to ChemCons, which is a normalization, which is an alternative normalization scheme. And FF stands for our proposed camera normalization. We also tried different crop strategies where we basically take crops at random or from the center. Now, what we see is actually C-log and RMSE scores. And for example, for when we report RMSE on methods trained with our planet scale depth dataset, as the scale is arbitrary when trained on MegaDepth, this is not a really dark comparison that's possible. So the best result is highlighted in bold numbers, as can be seen. And we can see that throughout testing on different other data sets like KITTI, Cityscapes, Diode, and of course MegaDepth for Make3D, we're actually obtaining quite favorable error results in comparison to the others, or error numbers. Because we're actually using structure from motion, and in the structure from motion, we're exploiting our recognition algorithms to mask out dynamic objects. We also are interested in analyzing the behavior of depth prediction for dynamic objects. Here are 2 example predictions that we have obtained on the KITTI dataset. On the top left, you can see a driving car, and on the top right, you can see a cyclist. And in the corresponding depth images, one can see that there's still ways for the network to pick up that training data, because particularly for parked cars, those still preserve the shape and will not be removed from all the cleanup phase after the patch match stereo algorithm. We also have numerical results presented on the bottom here. So the first is basically training only on MegaDepth and only on our data set. And we disentangle the different results for static and dynamic objects. And on the bottom, you see the same after fine-tuning on KITTI data. One very exciting result is that now for more than 7 months, we're on the top of the KITTI dense depth prediction leaderboard. And this is really due to the data set that we're proposing here. Let me also show a quick video. The video shown here is actually one that has nothing to do with our data. So this is data that comes from the Berkeley Deep Drive dataset, so the BDD 100K dataset. So the video on the left shows the depth prediction, and on the right, we have the original RGB image, which again, none of that data has been seen before. Okay, so the second part of my talk deals about learning multi-object tracking and segmentation from automatic annotations. The task of this problem is actually to learn joint multi-object tracking and instance segmentation. And what we want to do is, for the task of tracking, usually while this is done by using only bounding boxes, we want to exploit information that we obtain from instance segmentation algorithms, because that actually should allow us to improve the tracking results, because it's a finer delineation of objects of interest. However, ground truth data is very rare, and the task is actually fairly new. And obviously, if you have to annotate instance segmentation results or labels, provide those labels, that is expensive and time consuming. So what we propose here is actually a completely automated way of generating multi-object tracking and segmentation annotations from any type of street level video. In addition, we introduce a new architecture that's called MOTSnet, where we have a particularly interesting contribution that we coin mask pooling, and that allows us to actually achieve state-of-the-art results on all available data sets. In a nutshell, what we're doing is we're again building on top of panoptic segmentation results that were obtained by training on our Mapillary Vistas dataset. We're also using an optical flow network, but that optical flow network is being trained in a supervised way based on data that we could actually generate from our SFM pipeline. I will discuss this in more depth later. And finally, we're introducing a matching scheme that allows us to connect object tracks over time, such that we're actually able to not only derive the segmentation results in an unsupervised way, but also estimate the tracking data in an automated way. So one of the reasons that might come up is, why would you actually trust segmentation results from state-of-the-art result or from state-of-the-art methods? And one particularly interesting feature is when we look at high definition and high quality results from panoptic segmentation outputs. This is, for example, one that we just recently produced and that we were able to exploit for this automatic generation of MOTS data. You can see that the kind of results are actually pretty decent. Obviously, there are still some errors, but since it's applicable on a very large set of input data, it's actually something that helps us to overcome a number of limitations. And this is also because of the way how we designed our neural network to learn multi-object tracking and segmentation. Before we come to that part, let me also quickly go over optical flow. So for those of you who might not be familiar, optical flow is actually a way to obtain apparent 2D motion of pixels in image pairs. And that 2D motion is obviously very informative about how objects are moving in an image. Now, when we run a comparison with respect to structure from motion, what we have is optical flow actually works with static cameras. We can establish dense pointwise correspondences. And usually from 2 consecutive images, this is what people are using, while there's also existing multi-frame methods for optical flow. I will not discuss this slide in detail, but it gives basically just a simple overview of current state-of-the-art optical flow networks. In our case, we've actually been building on top of HD3, which is a recently introduced optical flow network, and delivers state-of-the-art results. Now, one important piece is, where do we get the training data from? No? You can see that I'm showing again a slide that I was showing just a few minutes ago for the depth data set. And eventually, when we run the filtering step on the produced SFM, or in our SFM pipeline and the patch match pipeline, when we generate the depth data, we also know that for those points that remain in the final clean depth, we do have visibility of the same pixel positions in many different neighboring images. So what we can do is, given the camera positions and the pixel correspondences, we can actually derive the flow information in an automated way. The second part of how we eventually use the flow information turns into the final tracking, turns actually into the tracking result. Now what we have is, we are considering detection results obtained on 2 different point in time. The first one is a segment that in the past frame, and the second could, for example, consider the segment in the current frame. And given the optical flow information, we can actually warp the segments into a joint reference system. And based on that system, we can generate a payoff for an assignment problem that we're about to solve. And that payoff is comprising 2 terms here. One of them is the intersection over union that we measure based on the warped segment and the segment at time t. And we additionally impose a number of constraints that, for example, requires the segments to have matching labels, that needs to determine whether those segments have suffice a minimal overlap, and also some additional sanity checks for the largest and second largest segments. So this is a slide showing our actual MOTS-net architecture. One can see that this is actually closely related to the mask RCNN architecture that's well known. What we've been doing is attach a so-called tracking head. And the tracking head is exploiting information that's produced in the instance segmentation or region segmentation head, eventually producing an embedding vector that we use during inference to run a matching procedure for segments that are detected and to get those associations over time. The tracking head is shown in more detail here. So as opposed to conventional tracking, which is usually done on top of bounding boxes, we have this additional information from the instance segmentation results, right? And that information gives us a much more fine-grained answer about how an object looks like, because it finer delineates the actual outline. What we're developing is something very simple, and we call this mask pooling. So essentially everything that's part of the instance mask is being used in a pooling layer in order to produce features which we eventually turn into embedding vectors and furthermore use during inference in order to connect detected segments over time. During training, we add an additional hard triplet loss for the tracking head, and that hard triplet loss eventually tries to learn object-specific embedding vectors, which are supposed to be similar for the same object over time, but dissimilar with respect to all the other ones. On the bottom, we can see a TSNE plot or visualization in 2D and together. So basically the third dimension is the evolution over time. What we want those embeddings is to stay basically very close to the ones from the previous frames, such that it's easy to actually associate instances over time. In our experimental setup, we're testing on every available MOTS dataset, which is the KITTI MOTS data and MOTS challenge. Both of them are fairly new. They've been announced last year at CVPR. And in addition, we're running experiments on the BDD 100K dataset. Our plan is to first estimate the quality of our automatically generated dataset, which we call KITTI Synth. And in addition, we show ablation results on the actual architecture. So KITTI Synth is something that's very impressive. So we can crawl this from all of KITTI raw data. We're using 142 sequences, excluding the validation set. And from 44,000 images, we produce something like 1.25 million object segments. On the top of this table, we can see if we just compare the automatically generated data against the human validated annotations in KITTI MOTS of the validation set, we're obtaining, for example, for cars, a MOTS score of 65.4 or 65.5, depending on the optical flow model used, and on pedestrians 45.7 or 45.4, which is very close to what state-of-the-art results were able to produce last year, but in a fully supervised way. We also run more ablation results to assess the quality of the mask pooling layer. And if we introduce additional pre-training on Mapillary vistas, we can introduce quite a nice gain in terms of scores. We also produce results on validation data in comparison to other data sets, to other methods, apologies, that were announced last year. We can again see that we are gracefully improving over those with our new mask pooling layer. Another data set we evaluate on is the MOTS challenge data set. We can see that the angle on is different, or the viewpoint of the camera. It's closer to pedestrians walking on a sidewalk scene. And when bringing the setup in a comparable fashion with respect to what was done last year, we're able to quite nicely outperform all the other works. Here's a short video about the obtained results on KITTI validation sequence. One can see that the segmentation and tracking results, tracking is indicated by keeping the same color, are actually very nicely preserved. We also have a very large variability of scale in objects that we recognize. And this is actually a video that we produced on top of existing BDD 100K data, where only bounding boxes are available. For more information, please drop by our virtual presentation of our poster on Wednesday and Thursday. And that brings me already to the end of this talk. So what is important for Mapillary is to use less supervision in the future and then instead exploit properly what we have been able to obtain from fully supervised methods that were developed in the past. We're in particular building on top of object recognition algorithms to improve single image depth estimation and multi-object tracking and segmentation tasks, because we were able to crawl and mine data at a very large scale based on the global pool of data that we have at Mapillary. Thank you very much for your attention. And again, I appreciate being invited as a speaker for this talk.